So I consider a system of two particles of masses. The previous class I started discussing about this case. Again, you just concentrate only to listen. Don't write the notes now. We will be given the notes later. We have considered a system of two particles of mass m1 and m2 which are separated by distance r, and each particle is initially at rest, and no external forces act on the system of the two particles, and the two particles start moving towards each other only due to the mutual internal forces between the two particles. Then as explained here, product of mass of the first particle displacement vector of first particle is equal to minus m2 into s2 bar. S1 bar is the displacement vector of first particle of mass m1 from its initial position. S2 bar is the displacement vector of second particle of mass m2. That means which are in opposite directions. So if you consider the magnitudes on the two sides, then m1 s1 is equal to m2 s2. So s1 is the magnitude of the displacement of the first particle from its initial position. S2 is the magnitude of displacement second particle of mass m2 from its initial position. Let us suppose the two particles collide with each other at the point P. That means S1, the distance moved by the first particle before the collision with second particle. S2 is the distance moved by the second particle before the collision with the first particle at the point P. Already earlier I discussed in the past, for a system of two particles of mass m1 and m2 separated by distance r, the center of mass system of the two particles lies in between the two particles on the line joining the two particles, such that the ratio of distances of the two particles from the center of mass will be equal to inverse ratio of their masses. And d1 plus d2 equals separation r between them. Here d1 is the distance of m1 from center of mass system. d2 is the distance of m2 from center of mass system. And the initial distance of m1 from center of mass system of the two particles will be equal to m2 r by m1 plus m2. This calculation I explained in the previous class. Initial distance second particle of mass m2 from it, the center of mass of system of the two particles. m1 r by m1 plus m2. You can observe from the figure on the left side, s1 plus s2 equal to r. And you solve these two equations. You get s1 equal to m2 r by m1 plus m2. s2 equal to m1 r by m1 plus m2. The comparison of the results I had discussed in the previous class and the results we got now, we can observe that S1 is same as D1, S2 is same as D2. That means if two point masses M1 and M2 are initially at rest, and if they are separated by certain distance R, such that no external force act on system, and if the two particles suppose start moving towards each other only due to the mutual internal forces between the two particles, then they collide at the position of the center of mass of the system of the two particles. And ratio of the distances covered by them up to in any instant before they collide with each other will be inverse ratio of their masses. In general, if you consider a system of two point masses M1 and M2, or two bodies of mass M1 and M2, which are initially at rest, separated by certain distance, and if they start moving only under the mutual internal forces between them, then M1 S1 bar you can write minus M2 S2 bar in vector form. S1 bar displacement vector of M1 from the initial position of M1 where it was originally at rest. S2 bar is the displacement vector of M2 from the initial position of M2 where it was originally at rest. Now I am going to show you the notes for the same discussion. So those who are writing the note, they can get ready with your notebook and pen. Come on, you can start writing the notes. Special cases, look at the screen here. Case 1. I will read out first. I have shown you the conclusion on the screen. Later I will be showing you the working part for the conclusion. That means I am just showing the notes for same special case one which I have just discussed now. So you can start writing the notes now. Look at the screen here. I will read out the conclusion statement first. I have given the conclusions first. The working for the conclusions is given later, because these conclusions we straight away use in some of the questions in objective type pattern. Consider a system of 2 point mass M1 and M2 which are initially separated by distance r and are initially at rest, such that no external force act on system. If they start moving towards each other due to the mutual internal force of attraction, then come on, first you finish copying the notes, writing the notes up to here. In case you need more time to copy the notes, you can take a pause and take your own time. I am going to show the notes continuation to this. First point A, you can write center of mass of system will be at rest. Same as the short form for center of mass. And second point B, ratio of the kinetic energies of the two particles at any instant before they collide with each other, same as the ratio of distances covered by the two particles up to that instant, which is equal to the inverse ratio of their masses. Come on, finish copying this. And third conclusion C, the two particles collide at the position of center of mass of system. Come on, finish copying the notes. In case you need more time to copy the notes, you can take a pause and take your time. I am going to show the working for these conclusions, which I have already discussed. Here F bar Ext is 0 bar. That means the net axial force on the system is 0. And VCM bar is constant. VCM equal to UCM. That means final velocity center of mass at later instant is same as the initial velocity center of mass at the earlier instant. At the beginning, both the particles are initially at rest, so initial velocity of each particle is 0. So initial velocity is the center of mass. Initial velocity center of mass system of the two particles is 0. So final velocity center of mass system of the two particles will also be 0. So center of mass is at rest. Center of mass system of the two particles is at rest. You can observe the diagram. Your O is of some fixed point. We choose it as origin on the line joining the two particles. To the left side of the two particles, M1 is the initial position. This represents the initial position of M1. This is the initial position of M2. I choose the line joining the particles as x-axis. Small r is the initial separation between M1 and M2. S1 is the distance moved with the first particle before they collide with each other. S2 is the distance moved with the second particle before they collide with each other. They collide with each other at the point P. Come on, finish copying up to here. In case you need more time to copy this part, you can take a pause and take your time. I am going to show the notes for continuation. I am going to show the notes for continuation for this. Initial distance of M1 from center of mass is equal to denoted by D1 equal to M2 R by M1 plus M2. This calculation we have discussed in the previous class. Initial distance of M2 from center of mass is equal to denoted by D2 equal to M1 R by M1 plus M2. Calculation for these two equations I have discussed in the previous class for system of 2 point masses. So P bar means total linear momentum system. We can write product of total mass system and velocity center of mass system. Here velocity center of mass system is 0. Our initial momentum of system is 0. Final momentum will also be 0. Final momentum system at later instant you can write P1 bar plus P2 bar. P1 bar plus P2 bar. P1 bar is linear momentum of first particle of mass M1. P2 bar linear momentum of vector of second particle of mass M2. So at any later instant during the motion under the action of mutual internal forces, we can write P2 bar equal to minus P1 bar. Or mod of P2 bar equal to mod of P1 bar, which we have denoted by P. So KE1 means kinetic energy of M1, you can write P square by 2 M1. KE2 means kinetic energy of M2, P square by 2 M2. Therefore, we'll get KE1 by KE2 equal M2 by M1. Come on, finish copying the notes. So in case you need more time to copy this, you can take a pause and take your time. I am going to show the continuation for this. So XCM dash equal XCM. That means final center of mass system is at rest. Therefore, distance of center of mass of system at the later instant before they collide with each other is equal to initial distance of center of mass system from the origin in the earlier diagram, which I have shown before. Here, this is the diagram which we are using for calculation. So here, from here, origin to M1, this is the initial distance of M1 from origin is X1. Initial distance of M2 from origin denoted by X2. X1 dash is a new distance of M1 from origin when it collides with P2. That means X1 dash you can write X1 plus S1. Similarly, X2 dash you can write it as X2 dash you can write X2 minus S2. So you can write M1 X1 dash plus M2 X2 dash by M1 plus M2 plus M1 X1 plus M2 X2 by M1 plus M2. Or M1 into X1 dash minus X1 equal to M2 into X2 minus X2 dash. X1 dash minus X1 I have written S1. X2 minus X2 dash is S2. That means S1 is the distance moved by M1 before the collision with M2, and S2 is the distance moved by M2 before the collision with M1. Or S1 by S2 you get M1 by M2 by M1, which is same as the ratio of the kinetic energies. The instant of collision S1 plus S2 equal to R. And S1 is to S2 is M2 is to M1. Come on, finish copying up to here. So in case you need more time to copy this, you can take a pause. I'm going to show the continuation for this. So you get S1 equal M2 R by M1 plus M2 and S2 equal M1 R by M1 plus M2. You can observe that S1 equal to D1 and S2 equal to D2. That means the two particles collide at the position of center of mass system of the two particles. So next I am going to discuss second special case. After copying up to here, again you please stop writing. Again you concentrate to listen. I will show the next notes for special case 2 later. First I will discuss the special case 2. So next I am going to discuss next special case 2 here. You can please stop writing here, you just concentrate to listen. I will show you the notes for this case separately. Instead of point masses, sometimes you may be given a similar situation, similar to what I have discussed in the previous case with two spheres. Let us consider one uniform solid sphere of mass M1 and radius denoted by capital R1. Let us consider another solid sphere of mass M2, another uniform solid sphere of mass M2 and radius denoted by capital R2. Let C1 be the initial position of center of mass of a sphere, C2 be the initial position of center of mass of the second sphere. Let us suppose the two spheres are initially at rest and they are initially separated by some distance d. That means d is the initial distance between center of mass of first sphere and center of mass of second sphere. Let us suppose each sphere is uniform. So center of mass of first sphere of mass M1 coincides with the geometric center C1 of the first sphere. Center of mass of second sphere of mass M2 coincides with geometric center C2 of second sphere. Let us suppose the two spheres are initially at rest and they are initially separated by distance d between their centers and no net external force acts on system here. So velocity center of mass system therefore remains constant. If each sphere is initial at rest, initial velocity of each sphere is 0, initial velocity center of mass is 0. So therefore velocity center of mass remains constant at 0. Means velocity center of mass system is at rest. I am going to discuss how to calculate the distance moved by one of the spheres before they collide with each other. So then the difference between the earlier case and this case is, in the earlier case, we have considered 2 point masses, and I said they collide at the point of center of mass. Here, they are considered 2 uniform solid spheres. So at the instant they collide with each other, the center of one sphere is separated from center of other sphere by a distance equal to distance between the centers of the two spheres at the instant they collide with each other will be equal to R1 plus R2, where R1 is the radius of first sphere and R2 is the radius of second sphere. I choose the initial position of center of first sphere as the origin of coordinate system for calculations. Let S1 be the distance moved to the center of first sphere before they collide with each other. And let S2 be the distance moved to the center of second sphere before they collide with each other. Here our center mass system of the two spheres is at rest. Therefore, XCM dash, we choose the line joining the centers of the two spheres as x-axis, and in each center of center of sphere, center of a sphere at the origin. Center of mass at rest, therefore XCM dash is equal to XCM. XCM is the initial distance of center of mass from the origin in the first case, when they are initial at rest, with the initial separation d between their centers. XCM dash is the new distance of center of mass system from the origin. Because center of mass system is at rest, distance of center of mass from fixed origin will remain constant. So XCM we can write M1 x1 plus M2 x2 by M1 plus M2. XCM dash you can write M1 x1 dash plus M2 x2 dash by M1 plus M2. X1 is the initial distance of M1 from origin, that is 0 because we are choosing the initial point of center of first sphere as origin. X2 is the initial distance center of second sphere from origin, that is equal to D. So X1 dash is the new distance of center of first sphere from origin, that you can written as S1. X2 dash is the new distance of center of second sphere from origin. So X2 dash you can write, you can observe from the figure, X2 dash can be written as S1 plus R1 plus R2. So we'll solve for S1 here on the left side. So you get M1 plus M2 into S1 plus M2 into R1 plus R2 equal to M2 into D. So you can solve for S1 from this equation. So M1 plus M2 into S1 can be written as M2D minus M2 into R1 plus R2. So distance moved by the center of first sphere before they collide with each other can be written as M2 by M1 plus M2 into D minus R1 plus R2. D is the initial separation between the centers of two spheres. R1 plus R2 represent the new separation between the centers of two spheres. So D minus R1 plus R2 gives you the decrease in the separation between the centers of the two spheres. or magnitude of the relative displacement of one sphere with respect to the sphere. After finding S1, if you are asked to find S2, from the figure you can observe S1 plus R1 plus R2 plus S2 can be written as D. So in case you are asked to find S2, can write S2 can be written as D minus S1 minus R1 plus R2. So next I am going to show you the notes for the same case here. So those who are writing the notes, they can get ready again with the notebook and pen. So next I am going to show you the notes for same case, that is for special case 2. First I have shown the conclusion on the screen. Later I will be showing you the working part for this conclusion. Come on, all of you look at the screen, copy this conclusion. I will once read out the conclusion. Consider two uniform spheres of masses m1 and m2, which are initially at rest with an initial separation small r between their centers, such that no external forces act on the system. They start moving towards each other under the action of mutual force of attraction. When the distance moved by the first sphere before they collide with each other is given by S1 equal to M2 into small r minus capital R1 plus R2 whole divided by M1 plus M2. Come on, finish copying this conclusion first. I will show the working for conclusion next. Problem based on this case was given one of the previous entrance examinations, the medical entrance exam in the All India level entrance papers. Come on, finish copying this. In case you need more time to copy the conclusion, you can take a pause and take your time. I am going to show the notes for working part for this conclusion, where capital R1 comma R2 are the radii of the two spheres. For coming to the working here, F external force, net external force system is 0, velocity center of mass system is constant. Initial velocity center of mass system of the two spheres is 0, so final velocity center of mass system of the two spheres is 0. So center of mass system of the two spheres is at rest. So in just like in previous case, here also you can say at any instant during subsequent motion, the clear amount of the two spheres will be equal in magnitude but oppositely directed. So the ratio of their kinetic energies at any instant before they collide with each other will be equal to inverse ratio of their masses. You can finish writing, copying this part. In case you need more time to copy this, you can take a pause and take your time. I am going to show the notes continuation to this. You can see the figure here. In the figure, this is the initial position of center of a sphere. This is the initial position of the center of second sphere. Small r is the initial distance between the centers of the two spheres, which are denoted by D. In the previous discussion, here in the figure it is denoted by small r. You can write D also instead of small r. Makes no difference. F bar 1 to F bar subscript 1 to represent the force of attraction on M1 by M2. F subscript 2 1 represent the force of attraction on M2 by M1. These dotted circles represent the positions of the two spheres, cross sections of the positions of the two spheres at the instant they collide with each other. S1 is the distance moved by center of first sphere before the collision of the second sphere, and S2 is the distance moved by center of second sphere before the collision with first sphere, which you have in this diagram. I have shown some origin to the left side of the center of first sphere. X1 is the initial distance of center of first sphere from origin. X2 is the initial distance of center of second sphere from origin. X1 dash is the new distance of center of first sphere from origin at the instant of collision with the other sphere. X2 dash is the new distance of center of second sphere at the instant of collision with the first sphere. You can observe from the figure x1 plus s1 equal to x1 dash, or you can write x1 dash minus x1 equal to s1. And you can observe from the figure x2 dash plus s2 equal to x2. That means x2 minus x2 dash can be written as s2. Come on, finish copying the diagram. In case you need more time to copy the diagram, you can take a pause and take your time. I am going to show you the calculation, continuation for this working. XCM dash equal XCM because center of mass system is at rest, distance of center of mass from origin remains same. XCM we can write M1 x1 plus M2 x2 by M1 plus M2. XCM dash we can write M1 x1 dash plus M2 x2 dash by M1 plus M2. So M1 into x1 dash minus x1, you get M2 into x2 dash minus x2. So you can cancel M1 plus M2 the denominator on the right side. So you get M1 S1 equal to M2 S2. X1 dash minus x1 is S1, x2 minus x2 dash is S2. So S1 is the magnitude of the displacement or distance moved by center of a sphere before the collision with second sphere. S2 is the magnitude of the displacement of second sphere or distance moved by center second sphere before collision with first sphere. S1 by S2 you will get M2 by M1. By this calculation which should discuss previous case, here also you can see the ratio of the kinetic energies at any instant before they collide with each other will be equal to inverse ratio of their masses. Come on, finish copying up to here. So in case you need more time to copy this, you can take a pause and take your time. At the instant of collision, S1 plus Kepler R1 plus R2 is equal plus S2 equal to small r. Small r is the initial distance between the centers of two spheres. S1 plus S2 can write small r minus Kepler R1 plus R2. S1 is M2 is to M1. You can solve the last two equations. You get S1 equal to M2 into whole multiplied by small r minus Kepler R1 plus R2 by M1 plus M2. Come on, finish copying up to here. In case you need more time to copy these notes, you can take a pause and take your time. So next I am going to discuss special case 3 here. All of you please stop writing, just concentrate only to listen. I will give you the notes for this case 3 later. You find number of questions in different books based on this special case 3. I mean you have number of questions based on similar logic or similar calculation in different books and also in the previous entrance exam papers. That means I consider a person, a boy or man, or a person of mass small m, standing initial at rest on a boat of mass capital M, which is initial at rest and floating in still water lake. And here is the shore. Okay, the friction between boat and water is negligible here. The man, suppose, begins to walk on the boat. A small distance relative to the boat toward the shore. The common observation, the boat will start moving in the backward direction. Because here we consider the man and the boat together as one system. The total weight of this system is balanced by the upward force of buoyancy exerted by the displaced water on the boat, on the system of boat and man. So here no external force are acting on system. Therefore total amount of system is constant. If the initially both the man and boat are at rest, initial amount of system is 0. Because initial loss of each mass is 0. So final amount of system will also be 0. So the vector moment of two masses becomes 0 when either each mass is at rest or they must be moving in opposite directions with same magnitude of momentum. So if the man begins to walk on the boat toward the shore, the boat starts moving in opposite direction with the same magnetic momentum. When the man stops on the boat, P1 becomes 0, P2 also becomes 0. The boat also stops. That means the man moves toward the shore, comes more nearer to the shore. Due to what? I mean, the man remains on the boat here, does not jump into water in the present discussion. So the man walks on the boat toward the shore. The boat will move in the opposite direction. The man stops on the boat. Man stops relative to shore. The boat will also stop. I'm going to discuss how to calculate the distance moved by the boat in the backward direction away from the shore. When you are given the distance which the man walks on the boat relative to the boat. Similar method you have to follow even those problems where instead of boat you may be given a trolley. That means our examples, the man may be standing near one end of a plank or a trolley which rests on a horizontal rails which offer negligible friction. Let us suppose friction between the rails and the trolley is negligible. Here capital M we use for mass of the trolley and small m for mass of the man. Both the man and trolley are at rest. The man begins to, then that means total external force on the system is 0. The friction force on the trolley, that is on the wheels of the trolley by the floor, is negligible here. By the rails is negligible. But of course there will be friction between the feet of the man and the plank or trolley. But when you consider man and trolley together as one system, the contact forces, the normal reaction friction forces between the man and trolley should be treated as internal forces. Internal forces play no role in the motion of center of mass system. That means whatever calculation I am discussing for this case on the left side, man standing on a boat, same calculation or same method has to be followed even for those problems where you are given that the man is initially standing at rest on a trolley of mass capital M, which is initially at rest, and the trolley is resting on two rails which offer negligible friction. The man begins to walk on the trolley in one direction. The trolley starts moving in the opposite direction. When the man stops, the trolley will also stop. So I am going to discuss the calculation for this case. Where similar calculation apply here also. You have find number of examples based on this case 3 in different books. So to let O be the some fixed point near the shore which we choose it as origin of the coordinate system. Just concentrate only to listen. I'll show you the notes later. For those who are interested to write the note, they can write the notes later, not now. Let C1 be the initial point center of mass of the man. C2 be the initial point of center of mass of the boat. Let's drawing a separate figure here. So let C1 be the initial position of center of mass of the man or person standing on the boat. Let C2 be the initial position of center of mass of the boat or trolley when both are initially at rest. As I discussed, the man walks some small distance linearly on the boat toward the shore. Where is the origin? Some fixed point near the shore. Let C1 dash denote the new position center of mass of the man or person standing on the boat. C2 dash is the new position center of mass of the boat or trolley on which the man stands. Man moves on the boat toward the shore linearly. The boat moves in the backward direction. That means distance between C1 and C1 dash gives you the actual distance moved by the man relative to the laboratory frame. of reference or with respect to shore. Distance between C2 and C2 dash gives you the actual distance moved by the boat with respect to station observed on the shore. Let x1 denote the initial distance of center of mass of man from the origin. Origin means some fixed point at the shore. Let x2 denote the initial distance center of mass of the boat from the shore or origin. X2 dash is the new distance of center of mass of the boat or trolley from the origin. X1 dash denote the new distance of center of mass of a man or person from the origin. You can observe from the figure x1 minus x1 dash equal to s1. x2 dash minus x2 will be equal to s2. Because using the same logic which we discussed in the previous two cases, here also net external force on system is 0. Total motor system is 0. Velocity center of mass is constant and velocity center of mass is 0. Center of mass of system of the two bodies is at rest here. Using the same logic and reasoning which we discussed in the previous two cases. Therefore, new distance center of mass from the origin will be same as the initial distance of center of mass from the origin. Xcm dash equal to Xcm. Xcm can be written as m1 x1 plus m2 x2 by m1 plus m2. Xcm dash you can write m1 x1 dash plus m2 x2 dash by m1 plus m2. So m1 plus m2 get cancelled both sides. So you can observe that here m2 into x2 dash minus x2 equal to m1 into x1 minus x1 dash. You can observe from the figure x1 minus x1 dash is s1. x2 dash minus x2 is s2. So therefore m2 s2 equal to m1 s1, or we write m1 s1 equal to m2 s2. Here as far as the magnitude of the actual displacement of the man with respect to stationary observer on the shore on the earth. S2 is the magnitude of actual displacement of boat relative to the stationary observer on the shore. M1 is the mass of the man. M2 is the mass of boat or trolley. Now magnitude of relative displacement of man with respect to the boat and magnitude of the relative distance with the man moves relative to the boat. Because the increase in the separation between the centers of mass of man and boat. C1 dash distance between C1 dash and C2 dash minus initial distance between the centers of mass. That means increase in the separation. Increase in the separation between the centers of mass of man and boat. This is the relative distance which a man walks on the boat with respect to the boat. Distance between C1 dash and C2 dash you can observe from the figure. Can be written as distance between C1 dash to C1 plus distance between C1 and C2 plus distance between C2 and C2 dash. Can C1, C2 gets cancelled here. Distance between C1 dash and C1 gives you S1. Distance between C2 dash and C2 gives you S2. That means the magnitude of the relative displacement of man with respect to the boat is equal to S1 plus S2. So magnitude of the relative displacement of man with respect to the boat or trolley is equal to sum of the magnitudes of actual displacements of man and boat. We can solve these two equations. You can observe from the first top equation S1 is to S2 is M2 is to M1. So S1 can be written as M2 by M1 plus M2 into S1 plus S2 means magnitude of relative displacement. S2 can be written as M1 by M1 plus M2 into Magda related displacement. In the present discussion, we discuss M1 mass of man by small m, M2 by capital M. That means Magda the actual displacement of the boat or trolley is equal to small m by capital M plus small m into Magda related displacement. Next, I am going to show you the notes for the same case 3. Now, I will show you the conclusion directly. After showing you the conclusion, first you copy the conclusion. After copying the conclusion, then you can copy the working part for the conclusion. Come on, get ready with your notebook and pen now. Come on, look at the screen here. I am going to show you the notes for the case, special case 3, which I have discussed, which is the most important special case in this chapter. We find number of questions based on this case in different books and also in the previous entrance exam papers. Look at the case 3 here. First, I am going to read out the conclusion first. You can copy this in your notes. Later, I will show you the working for the conclusion which I have discussed. Consider a man of mass small m standing on a boat within brackets or trolley resting on rails which offer negligible friction. Close the bracket. Again, I repeat here. Consider a man of mass small m standing on a boat of mass capital M, floating in water such that system is initially at rest with respect to the shore, and velocity of water is negligible. That means you may assume that friction between boat and water to be negligible here, so that you can assume that net axial force on system in the horizontal direction is 0. In the vertical direction, the total weight of system is balanced by the force of buoyancy or normal reaction by the rails in the case of man standing on the trolley. If the man walks rectilinearly on the boat, here you should write if on the left side. Again, repeat the last sentence. If the man walks rectilinearly, means moves in a straight line path on the boat or trolley, a distance S subscript REL with respect to the boat within brackets or trolley, the actual distance moved by the boat within brackets or trolley in the opposite direction is given by S subscript boat equals small m by capital M plus small m whole multiplied by S subscript REL. Come on, copy down this conclusion first in your notebook. In case you need more time to copy this conclusion, you take a pause and take your time. I am going to show you the continuation to this. Working here. See the figure here. C1 is the initial position of center of mass of the man. C2 is the initial position of center of mass of the boat or trolley. C1 dash is the new position of center of mass of the man after he walks some distance on the boat. C2 dash is the new position of center of mass of the trolley or boat, which will be displaced away from this shore. S1 is the actual distance moved by the man relative to the stationary observer on the shore. S2 is the magnitude of the actual distance displacement of the trolley or boat with respect to stationary observer on the ground. X1 is the initial distance of man from the fixed point 1 on the shore as origin. X1 dash is the new distance of the man from the origin or shore. X2 is the initial distance of center of mass of the boat from the origin, and X2 dash is the new distance center of mass of the boat from origin. Come on, first finish copying the diagram here, because all the working depends on this diagram, based on this diagram. So it's compulsory for you to copy this diagram to understand the discussion or calculation part. In case you need more time to copy this, you can take a pause and take your time. I am going to show you the notes for continuation, working part, calculation part for this case. Here man and boat we are considering as one system. Net axial force on system is 0. The velocity center of mass system is constant here. Initially, both the man and boat are at rest, so initial last center of mass system of the man and boat is 0. And final last center of mass system of the man and boat will be also 0. So center of mass system of the boat and man is at rest. And vector sum of the linear momentum system of the man and boat is 0. That means P1 bar plus P2 bar is 0 bar. So P1 bar equal minus P2 bar. That means when both the bodies total momentum is 0 means both the bodies are either at rest or they may move in opposite directions with same magnitude momentum. So man begins to walk on the boat or trolley linearly toward the shore. The boat or trolley starts moving away in the opposite direction with same magnitude momentum. When the man stops, the boat or trolley will also stop here because the resultant momentum system is 0. Come on, finish copying up to here. In case you need more time to copy this, you can take a pause and take your time. So xcm dash equal xcm. Xcm is the initial distance center of mass from origin. Xcm dash is the new distance center of mass from the origin. Xcm you can write m1 x1 plus m2 x2 by m1 plus m2 on the right side. Xcm dash you can write m1 x1 dash plus m2 x2 dash by m1 plus m2. You can cancel m1 plus m2 in the denominator on the right hand side. So you can write m2 into x2 dash minus x2 equal m1 into x1 minus x1 dash. M2 S2 equal M1 S1. So magnitude of the relative displacement of man with respect to the boat is equal to distance between C1 dash and C2 dash minus distance between C1 and C2. That means whatever calculation I have explained earlier, same thing is shown on the screen here. Come on, finish copying. In case you need more time to copy this, you can take a pause and take your time. So from first and second equations, you get simplification as explained, you get finally the same conclusion. Come on, finish copying the notes. In case you need more time to copy this, you can take a pause and take your time. I will be discussing a problem based on this case in my next class.